Finally, we have actually a technique called Picnophylactic Interpolation. And we won't do any of this, but I'm just showing you what it would look like. Picnophylactic interpolation basically takes the strong boundaries between administrative units and their values, and you can see that in the 3D view right here in the middle case. So you see these strong, basically cliffs, so very abrupt changes in value, because there might be 10 people here, 9 here, and 4 here. And because of that, you have these very abrupt changes at the boundaries. And we know that's not realistic, and so Picnophylactic interpolation will smooth, according to how much you want to have it smooth. It will smooth the abrupt boundaries by basically smoothing out the interpolation, or the smoothing out the values between administrative units, polygons, while at the same time maintaining the original volume within each polygon. So for example, here, just above that, we see this is a pycnophylactic view of the same region. And this polygon right here is represented right here, kind of. And if you sum that within the boundaries of the original polygon, you will get the same number, the same count. So if there was 10 here, you'll still get 10 here within the boundaries, even though the boundaries at the edges are no longer sharp and they bleed or gradually change into boundaries of the next polygon. And so it's called Picnophylactic interpolation because it's volume preserving at the polygon level and, of course, at the level of the entire map as well. So it has the following properties. First, it creates a smooth surface with no steps, and attribute values should not change suddenly at zone boundaries. So we know in the real world, well, the zones are artificial often, and we don't expect that the boundaries actually are hard cutoffs between whatever processes we're observing within the polygons. The total value of the attribute within each source remains constant. Undertaking Picnophylactic interpolation in GIS is just an iterative procedure, and it's best done with, obviously, with raster, not with vector data. And so basically you create a raster polygon zones. So you take your original polygon layer, like it's a vector layer, for example, and you rasterize it. So you encode it into polygon, or into raster cells, where each cell has the same identifier, zone identifier, as the polygon in the vector data. And then you calculate the density of a count variable, whatever one you want. You convert that density to raster and to counts per cell, so that every cell gets an actual count amount rather than just a density amount. So every cell then, if you summed up every cell in the layer, it would be equal to the original count of the sources. Then you create a raster layer containing the total counts per zone. So that means doing a zonal statistics. So zonal stats. Then you smooth the values by replacing each cell's value with the average of its neighbors using a mean filter. So there's their neighborhood or focal stats, a focal mean. And then you sum all the values of the cells from here in each of the zones. And of course, at that point, after doing the mean filter, the sum of the values in each of the zones aren't going to be the same as the original polygons because you smooth them. So then they're adjusted in this last step here. You adjust the values that have been smoothed within each zone proportionally so that the zone's total is the same as the original total of the input itself. So for example, the total is 10% low, increase the value of each cell by 10%. And then you repeat these steps 5, 6, and 7 over and over again as many times as you want to get as smooth of a surface as you want. So these ones get repeated in a cycle. This is an example in Python, just showing the initial zonal configuration. So these are the zones of, I can't remember which, these are just zones. I think it's probably dissemination area zones to start with here. And then we have the total counts here. So we take whatever values are in the zones and we apply them to the relative regions. So if there was, within this zone here, you can see that's a straight up zone, or was a zone, that's this zone right here. However many people are in there are now equally distributed to each cell within that particular zonal configuration. And then there's the Python and the iteration here that goes through that, which you could try if you want. And in the end then, we have from that original population density that has the very sharp boundaries like that, after iterating 40 times, looks like that. So you see it starts to get more, the boundaries aren't as sharp anymore. They've blurred a bit. More iterations will make, so that's 10 iterations. And then more iterations will increase that further. 20 iterations, 30 iterations, and 40 iterations. Now you see how areas like this become much more soft in terms of their boundaries. There's no longer sharp boundaries anywhere. And of course, you go even more iterations if you want. There's no right or wrong answer as to how smooth you should go.